Welcome back to week 4 of Applied Business Statistics. This time we're going to be doing the first of our real hypothesis tests. And we're going to look at a type of hypothesis test that is a little less common, but it has a very specific application for business. So it's really important that we know how to do a variance test. For this to make sense, I want you to imagine that you're working at McDonald's. And specifically, you're working at the coffee station. A customer comes in, orders a cup of coffee. You push the button on that machine, and it should dispense 12 ounces of coffee. But we know that there's always going to be some variability. Some cups might get 12.1 ounces, some might get 11.9. You know how when you fill up a coffee cup, the machine drips a little bit. There's going to be a few drops more or fewer. There is always going to be some variability, but it should be somewhere really close to that average of 12 ounces. So we have a point estimate of 12 ounces, and then we have some variability around that point estimate. So why does variability matter? You've probably seen packaging where it says something like, contents may settle, sold by weight and not by volume. And then when you look at the specifics about the weight, this package contains 24 ounces. So you can be confident that even if it looks like it's 3/4 filled, really this container, contains exactly what it says on the label. But I guarantee if we looked at enough of these containers, we'd find that it's close to 24 ounces, or if we looked at enough coffee cups, close to 12 ounces, but not every one is going to be filled exactly the same. There will always be some variability around any of these fills or point estimates. Variance, which is what we're going to be talking about, is how much something deviates from an expected value. If you expect 12 ounces in the cup, you should be getting really close to that, but some will be a little more and some will be a little less. We can plot the variability, we can calculate the standard deviation, and what we will find is there are some distributions that have high variability and some that have low variability. Now in this example, the average is 12 ounces, but this distribution has low variability, which means it's very consistent. It might be slightly more or slightly less, but it's consistently right around that 12-ounce average. On the other hand, if we have high variability, we have much deviation from that norm. And this can create problems because it's not consistent. That 12-ounce pour of coffee is probably not going to be 12 ounces. We're going to count on it being too much or too little. What we want to know is whether that coffee machine is performing consistently. Variability is the opposite of consistency. Now, why does consistency matter? Because in business, it's important that people know what to expect. And a great illustration of minimizing variability is the McDonald's Corporation. So let's imagine that we're going on some kind of road trip across the country. And we're going to stop at every McDonald's that we pass, and we're going to sample the hamburgers along the way. You may remember this picture from, if you've ever traveled to Oklahoma City from Springfield. You remember the world's largest McDonald's? It's still there. The paint job is a little different than it used to be. It doesn't look quite like this. Turns out the world's largest McDonald's is really the same size as every other McDonald's you've ever been to. The McDonald's part is just the same, but the building that it is in is quite large and it spans the highway. I remember the world's largest McDonald's as having the world's nastiest bathrooms when we stopped there on our road trip going through Oklahoma. So I'm hoping they've improved on that. It's got nothing to do with the McDonald's people. But I do remember stopping there at McDonald's and looking out at the cars passing underneath on the highway as we sat and relaxed a little bit before we got back on the road. Every time we pass a McDonald's, we're going to stop or we're going to get a hamburger, or we're going to get something. And what I want to know from you is, if we were to stop at a McDonald's in California, in Kansas, in Mississippi, in New York, what do you predict about the taste and the texture, the experience of a hamburger from any of those places? Is the variability going to be high, or is the variability going to be low? And the answer is, the variability will be low. It will be very consistent. Every hamburger tastes like every other hamburger you've ever had. High consistency means that people know exactly what to expect. The reason this matters for business is because consistency builds trust with your customers. Whether or not people like a particular product, so maybe you love McDonald's hamburgers, maybe you don't, but you always know what to expect. And that is a selling point. You're never disappointed, you expect it, and that's exactly what you get. If you try to run a business where people expect one thing and they are consistently either getting too much, too little, it's different than what they expect, that tends to not be great for business. So we want to have good consistency no matter what the product is. What I would like to be able to do is check every machine, every pour in every McDonald's across the world, but that is unrealistic. So I'm not going to try to test the whole population. What I'm going to test is a sample. I'm going to draw a smaller subset from the population and then use what I learn from that sample to apply back to the population. If I have data, I can calculate a sample variance. I can do this very easily in Excel. I can just use a formula to give me the variance of this sample. Once I have that variance, which by the way is written as either S squared or sometimes SD squared, once I have that value, I can use that as an estimate for my population. The true variance of the population of all McDonald's coffee machines across every location nationwide would be expressed as sigma squared, that Greek letter telling us that this is a population parameter. This is a value for a population. I haven't measured sigma. I haven't measured the whole population. I've used a sample that will be my point estimate of the population value. The distribution of the variances in a sample is going to follow a chi-square distribution. So what that means is we know what to expect, and we'll base our expectation on the sample size. More specifically, the number of degrees of freedom in our chi-square, which is going to be n minus 1. So what I could do if I have a sample of 50, that would have 49 degrees of freedom, n minus 1, and I could plot out a chi-square distribution and then use that for making inferences later on. The variance from the sample can be used for three things. I can use the variance from my sample to estimate the population variance. What is true of the sample should be true of the population from which it was drawn. Therefore, I can extrapolate from what I know from my sample, its variance, to the variance of my population. The second thing I can do is then calculate my level of uncertainty. How confident am I that the estimation that I've just done from sample to population is really accurate? And the fact is, I'm going to be more confident if that estimation came from a large sample than if it came from a very small sample. I will then explain my level of confidence in a confidence interval, which will show where that mean estimation would fall 95% of the time. And then what I can do is take that sample variance and use that for a hypothesis test. The hypothesis test is going to be based on a population value, and typically what that is going to be is whatever standard we have for the outcome. Specifically, if the cup says 12 ounces, then the standard we're shooting for is 12 ounces of coffee in that cup every time the machine dispenses the coffee. I could then use a sample and measure whether the variance of that sample is consistent with the variance of the population that we have stipulated as the amount, the tolerance that we have for how much variability there's going to be around that 12-ounce mean. The standard deviation is the square root of the variance. So variance and standard deviation are very similar measures of variability, but I want to distinguish between them so that when you see standard deviation, you know that that's not a different thing than variability. It's just the standard deviation, the square root of the variance or the variability. The first thing that I want to be able to do is to create a confidence interval estimation for any particular value that I have estimated. For this example, we're going to use the McDonald's quarter pounder. The quarter pounder was introduced in 1971. And I remember, because I was alive back then, not too long after it was first introduced, people kept saying, you know what, it's not really a quarter pounder. The pre-cooked weight was 1/4 pound, but after it had been cooked, it always weighed less than 1/4 pound. And McDonald's finally adjusted that. They increased the size of the quarter pounder pre-cooked weight to 4.25 ounces or 210 grams, so that after cooking it came in right at that quarter pound average. McDonald's has a machine, I'm sure lots of machines somewhere, that they use to make these hamburgers. Now that machine is dialed in, calibrated to always create hamburger patties of 210 grams. But just like the coffee maker, there's always going to be some variability around that 210. Knowing that, there's a level of tolerance for how much variability there will be around that 210 gram average. A little bit more, a little bit less, that's within tolerance. But if the machine gets out of whack, if it is miscalibrated, well then we could have too large or too small of a hamburger patty, and that could be a problem. It's inconsistent. People are not going to like that. That is not the McDonald's brand. McDonald's is built around consistency. So what we want to do is gather a sample, test that sample, take what we learned from that sample, apply it back to the population, and determine whether this machine is working as it should. Is it within specification? We get a random sample of 24 quarter pounder patties. We measure how much they weigh. We calculate the variance around those weights, and we come up with a value of 0.0145 grams. Well, that seems pretty small, but what we want to know is whether that estimate that we've gathered from our sample is accurate to the population. So here are the steps we're going to go through. Number one, collect a sample. So we've already done that. The data for this are going to be in a spreadsheet that we'll be using here in a moment. Then we'll take what we learned from our sample, specifically the variance of that sample. We will calculate our sample variance, use that to estimate the population variance, and then say how certain or uncertain we are about that step 3 population variance estimate. So the way this should work is, what is true of the sample should be true of the population from which it was drawn. That's something we've talked about previously. Therefore, if I draw a sample, the variance in that sample should be really close to the variance of the population. But random error is going to mean that it won't always be. It should be close, but it's going to be off by a little bit. However, I only have one sample, so that's going to be my best guess as to the population value. On the other hand, if I have a small sample, it's not going to be as good a guess as if I have a large sample. So I will be more confident in my guess if I'm using a large sample than a small sample. So I can do two things. I can make a point estimate. I can say what I think is the population value based on the sample value, and then I can tell you how confident I am about that guess based upon the sample size. We're going to need both of those. If we have repeated samples, there is a range in which the true population value is going to fall 95% of the time. And this is called our 95% confidence interval. It'll work like this. I've already told you that we'll be using a chi-square distribution. It's based on the number of degrees of freedom or the sample size. So let's imagine it looks like this. What I would do is keep 95% of the scores in that distribution in the middle and create two cutoff scores in the upper tail and one in the lower tail that will correspond to some value on this number line, which will give me the lower confidence interval and the upper confidence interval. The way that we're going to do this calculation is to use Excel and a spreadsheet that I've given you for the class. Our research question is this: what is the 95% confidence interval around the population variance? How are we going to answer that? Well, draw a sample, calculate the variance of that sample, use that sample variance as an estimate of the population, and the sample size will give us a clue as to how confident we can be about our guess. So what I'd like you to do is open up this Excel spreadsheet and look for the One Sample tab. Now in this example, I have the data on a separate tab, which is labeled as data. But if you're doing a homework assignment or a test assignment, you'll have data from somewhere else, but you can still use this spreadsheet. And I'd remind you that the way that I've coded the spreadsheet, it works right now, but if you're doing multiple iterations, if you're using it for several different examples, you might want to close without saving and then reopen, or at least have a fresh copy of that spreadsheet available, because if you play around in it too much and you change some of the code or break something, it might not work as expected. We need some data. Let's go to the Data tab, which will be the tab, if you look at the bottom of your screen, furthest one on the right. Click on the Data tab, and we are going to grab the column that is labeled as weight in grams. Click on B for that column. It'll select everything in that column. And you can right-click and copy, and then jump back to the One Sample tab, and you'll see where those data are supposed to go. Click on that column header, right-click, and choose Paste. So you've now copied and pasted the information from the Data tab into the One Sample tab. What you'll notice is as soon as you copy and paste the data, the spreadsheet comes to life, and you can see the results from our sample. Let's take a look at what that would look like. We have a sample of size 24, which gives us 23 degrees of freedom. My confidence coefficient is set at 95%, and that's because the p-value is set at 0.05. If you want to change the confidence coefficient, let's say to 90%, you would change this p-value in red. Don't change the confidence interval directly, because that'll mess up the coding. Just change the p-value from 0.05 to 0.1, and now you would have a 90% confidence coefficient. The findings will be down in the blue box. So we have our mean, our sample variance, there's that 0, 1, 4, 5, standard deviation, which will be the square. We have critical values for the chi-square, but the ones that we're interested in right now are the point estimate and the confidence interval around that point estimate. The point estimate of the population is always going to be the value from the sample. The sample variance, 0.0145. Therefore, the point estimate, 0.0145. However, we're 95% confident that the real population value is going to be between 0.0087 and 0.0284. Those are the lower and upper limits of our 95% confidence interval. And here is how we would write this up in APA style. We would explain what we've done and what we found. A sample of 24 quarter-pounder patties was randomly selected to measure their variance. The sample yielded a variance of 0.0145 grams. This measurement provided a 95% confidence interval around the population variance between 0.0087 and 0.0284 grams. So what you may have noticed in that spreadsheet was there was a space we hadn't used. It's about hypothesis testing. Now that's the area where we can plug in a known or an expected value, like a tolerance that we need to stay within, and we can test whether our sample is within that tolerance. So what we're going to do here is some hypothesis testing using our sample to estimate a population value. For this example, I'll use the McDonald's special sauce that they put on the Big Mac. And it's important to control costs, so they have developed a tool to make sure that the amount of special sauce added to the Big Mac stays around the 30-gram or 2 tablespoon value. So the special sauce gun is being used to dispense a precise amount of sauce, and if that variance is excessive, we're going to have to adjust this special sauce gun to get it back into tolerance. Of course, if there's just a moderate amount of variance, that would be acceptable, so we don't have to make any adjustments. The acceptable value is 7.5 grams. So our inspector collects a random sample of 36 Big Macs and how much sauce was on each one. We want to know whether the amount of sauce from our sample variance differs from 7.5 grams. This is a hypothesis test, so we'll start by choosing the appropriate test. I told you this would always be the easiest answer because it's whatever test I'm teaching you about right now. Of course, right now we're learning about a one sample variance test, which uses one sample, categorical, that is 36 Big Macs. And then we need a dependent variable, which will be at the scale level. That would be number of grams of special sauce from this super cool gun that they're using to dispense that. We have a categorical variable and a scale variable. The setup for that would then allow us to do this one sample variance test. Step 2, we're going to establish the null and alternative hypothesis for this test. The null hypothesis will be h sub 0 sigma squared, or the variance of the population, equals 7.5 grams. This sample is drawn from a population that has a variance of 7.5 grams. The alternative hypothesis, sigma squared, does not equal 7.5, or this sample is drawn from a population that does not have a population variance of 7.5, and if so, then this gun is out of specification. It will need to be adjusted. Step 3, select the criterion for statistical significance. Typically, we're going to stick with alpha of 0.05, but as we've already experimented with, we could change that to 0.1 or 0.01 to get 90 or 99% confidence intervals. The critical value is going to be based on a chi-square distribution, and the number of degrees of freedom will be n minus 1, where n is the sample size. You simply plug in the degrees of freedom, the n minus 1. Well, we have 36 in our sample. Degrees of freedom is 35. And then we get critical values for lower, upper, and two-tail. We're going to be doing a two-tailed test, so we'll be using this critical value of 49.802. And now we're ready to calculate the test statistic. And to do this, we'll be using Excel and that spreadsheet that I gave you. Our research question is, does the sample variance from store 1 differ from 7.5? So go to your spreadsheet, go to the Data tab, and find column E that has the data for store 1. We only need that single column. Click on the E header, which will select the entire column of data. You can right-click and choose Copy. Go back to the One Sample tab and paste that data into column A. You'll see the values that we had previously will change, but there's one more thing that you need to do to run this hypothesis test, and that is tell the software what value you're looking for. And in this case, the hypothesized value is 7.5. And then we get the probabilities. And of course, the probabilities are based on one or two-tailed test. In this case, we're doing the two-tailed test, so we'll be using the probability of 0.6725. Well, that is greater than 0.05. So this is not a significant difference. Now, that's good news. Our sample doesn't deviate from the population value. That's the expected value. That's what it should be. So what we have determined is that this sauce gun is working within specification. It does not statistically significantly differ from what we would expect. In this case, the non-significant test is really what we want to see. Step 5, interpret the results and write up the findings. Our critical value is a 0.49, but the value that we calculated for our chi-square was a 0.37. It did not get over the fence. The probability is a 0.67, which is greater than 0.05. The confidence interval of 5.35 to 13.84, that includes 7.5. So all three of these things are telling us exactly the same information, and that is that this is a non-significant difference. That's what we want to see. This sauce gun doesn't deviate from the population value. The variance in store 1 was not statistically significantly different than the 7.5 gram specification for distributing special sauce, non-significant, failed to reject the null hypothesis. And I could write this up in APA style to explain what I did and what I found. So far, we have been using one sample tests, comparing one sample to a population value. But if we have two samples, we can also compare those samples to each other. Although the test is going to change slightly. Well, instead of a chi-square, we're going to be using an f-test. So we will be able to make comparisons of two sample values. So when would this happen? Let's say we have a bus stop, and there is a bus that comes to the stop. It's supposed to be there every 10 minutes. Or you think of the shuttles that we have running on campus. They're supposed to arrive at a certain interval. And of course, they don't arrive exactly at that 5-minute or 10-minute or 8-minute interval. Sometimes it's slightly early, sometimes slightly late. There's variability around that arrival time. We could compare two different shuttle routes to see whether the variability on one or the other is greater or less. We have a machine that's supposed to make 6mm bolts. There's going to be tiny amounts of variability, but they better be really close to 6mm. They better be within specification, and we could compare two different machines to see whether they had greater or less variability if one of them was out of specification. We have two samples of light bulbs. You know, light bulbs are made by companies all around the world, and yet they all work in the light fixtures that you have at home because there are standards. And as long as your light bulb meets certain specifications, it's going to work within this light bulb environment. Well, if you're making light bulbs out of specification, they'll be too tight or too loose, they won't work. So we could compare machines that are making light bulbs to see whether one or the other is out of specification. Same idea for production ovens that heat to 350 degrees. We want to make sure that when they hit that 350, we don't have too much variation above or below that number. So here's how this would work for our McDonald's example. Delivery time. Walk-up customers should receive their order within 90 seconds. However, McDonald's has introduced kiosks where you don't have to talk to a human being. You can press buttons on a screen. Is the consistency of the delivery time the same between going to the walk-up window or the counter versus using one of these kiosks? The time for delivery was measured for 55 orders at the counter and 48 orders from customers using the kiosk. Now, there's an important thing we have to remember whenever we're using this test, and that is we need to check the variance first, and it matters the order in which we enter the variances. So we'll check the variances, and the larger variance we're going to treat as sample 1. The smaller variance will be sample 2. If you compare a third sample, that might change the order of entry. So be sure that you check first and then always put the larger variance into the formula first. So we're going to do a hypothesis test. We're going to begin by selecting the appropriate test. In this design, we have two samples, both of which are categorical. We have 55 orders from the counter and 48 orders from the kiosk. The number that we're looking for variability around would be time, so number of seconds for food delivery. Is there greater or lesser variability in one of these two samples? Step number 2, we'll establish an alternative hypothesis, which will be based upon the choice that we've made to use a two-sample variance test. The null hypothesis would be that the variability in these two samples is the same. And we would write that as h sub 0 colon sigma squared 1 equals sigma squared 2. The square in the upper right, that is referring to the squaring of a value. The 1 and 2 refers to the sample. So sample 1 has a sub 1 and sample 2 has a sub 2. Both of these samples are hypothesized to have the same variability or to have been drawn from populations whose variability is the same. The alternative hypothesis, h sub 1 colon sigma squared 1 does not equal sigma squared 2, that the variances between counter and kiosk are not equal. And now we select a criterion for statistical significance. We're going to keep our settings at an alpha level of 0.05, and we'll be using this time an F distribution instead of a chi-square distribution. Now, an F distribution has two different degrees of freedom. So it has the degrees of freedom within and degrees of freedom between. In this case, because we have two samples, we'll be using those 2 degrees of freedom based upon sample sizes. So for instance, the first sample will have n minus 1 as its degrees of freedom. The second sample, n minus 1 as its degrees of freedom. So what we will do is in the 2 sample tab, look for this box that says F distribution values, critical values, and let's enter these numbers in order. Our alpha level is going to be set to 0.05. The numerator, the first degrees of freedom, will be based on sample 1. Whatever its sample size is, it was 55, so there are 54 degrees of freedom in the numerator. For the denominator, a sample size of 48 gives us 47 degrees of freedom in the denominator, and that gives us a critical value with 54 and 47 degrees of freedom in an F distribution of 1.60. It's important to note that if you were to enter these 2 degrees of freedom in the opposite order, that would change your critical value. So it's very important that you keep track of which group is 1 and which group is sample 2 as you're doing this test. Step number 4 is to calculate the test statistic. And again, for this, we're going to be using Excel. So we want to answer a research question: is the variance on wait time different for the counter and the kiosk? So here are the steps that we'll walk through. Go to that Data tab. Get the 3 columns of data for counter, kiosk, and app. Select all 3 of those columns, copy, and then go back to the 2 sample tab and paste that data into the columns where they belong. The way that we're going to test this data is we're going to use something that's already included with Excel, and that's the Excel Analysis Tool Pack. To get to this tool pack, we're going to use the Data ribbon. So click on Data, and you now see the Data ribbon. On the far right end of that ribbon, you're going to see Data Analysis. Click on Data Analysis, and it will pull up a menu of possible analyses that we could run. Scroll up or scroll down until you find F-test 2 sample for variances. And then click OK. Now we need to tell Excel where the data are that we want to test. Remember, we're putting the larger variance in first. So for variable 1 range, you can either enter B:B or just click on the B tab to select that column. For variable 2, click on the column header A. So we have A as our variable 2 range. By selecting the header, we also need to let Excel know that there are headers in this data. So click on the Labels box, and we'll leave our alpha level set at 0.05. Finally, for the output range, click on Output Range, and then in the box, you can click on F2, and you can see where that drop zone is that I created for you. That's where we want our findings to go. Click OK, and we get the results of our F-test. They're going to look like these. So we can see our means, the variances, number of observations, degrees of freedom. Here's our F value. It's a 2.06. A probability of 0.006, statistically significantly different. There is a difference between these two mechanisms of ordering. So now we are going to interpret the results and write up the findings. Was this a statistically significant difference? Our critical value is a 1.6, but the F value that we calculated was 2.06. 2 is over that fence. It's further away than the 1.6, so it is significant. The p-value of 0.006 is less than 0.05. Less than a penny would be certainly less than a nickel. So our decision would be based upon these findings. The counter variance is statistically significantly larger than the kiosk variance. We would reject the null hypothesis. And we could write up our findings in APA style, describing what we did and what we found. All right, so with that, do you have any questions about what we've covered? Thank you so much for being here. We will have our lab day on Wednesday. So if you come back for lab day, I'll be happy to walk you through all of these steps if you have any questions at all. Thanks a lot. See you Wednesday.